just similar to the presentations that were given by our users, concluding with Zenoh-Flow, let's conclude this Zenoh user meeting with a short presentation about Zenoh-Flow. So my name is Julien Loudet, and I'm the project lead for Zenoh-Flow. So first, we didn't make a lot of noise about Zenoh-Flow, so let's give kind of a genesis. So where did we start with Zenoh-Flow? So we basically were contacted by a customer that asked us to create a distributed data flow programming framework based on Zenoh. The idea was to emulate this project that is developed by the University of Berkeley called Pilot. And our purpose was to replace the underlying data flow programming framework with Zenoh-Flow. Luckily, everything went well, and this is a simulation that we run. Where basically this is exactly the same logic. We just kept all the nodes, all the logic, just replaced everything with Zenoh-Flow to check that it was working. So our first approach, with better performance. So our first approach was successful. When we mean better performance, the main difference compared to their solution is that we didn't need to stop the simulator between every frame. So the Kala simulator sends us a frame. We are able to compute the steering and acceleration or braking that we need to give the simulator. And then by the time we send its information, it has time to send us the second frame and ever going. Obviously, this was not running the full machine learning pipeline, just the perfect perception. How is the deployment? So to deploy this Zenoh-Flow application, what we did is that downstairs in our servers, we have one virtual machine that is running the Kala engine simulator, and we had another virtual machine with the Zenoh-Flow, so everything, the Zenoh-Flow runtime. And basically, there was publishing and subscribing through Zenoh in order to send the information. So this is how Zenoh-Flow started. So after this first project, what are our motivation for Zenoh-Flow? So the first is, well, we already have today a distributed declarative data flow framework that gives you full control over the flow of your data. This flow, we strongly enforce it and work seamlessly on a single or multiple hosts. So this is the first basis. Then our motivation also is that, much like Zenoh, but this is even stronger for Zenoh-Flow, this is developed in Rust. So why Rust is important nowadays? Well, we're seeing many traction, especially in the automotive industry, to use a programming language that is memory safe, concurrency safe. We can see also that we have now the Ferrocene that released the first Rust compiler that is certified for ISO 26262. We also have testimonies from, for instance, Volvo engineers that think that Rust is actually a good idea for your car. Or lately, and it's created a little bit of buzz in the Rust community, the CTO of Microsoft Azure that says that for new development, it's time to use Rust instead of C and C++. So with these things going, we are also seeing that for autonomous driving applications nowadays, ROS is considered as the default, but it has some limitations. This is perfectly illustrated from a talk that the guys working at Cruise, so a subsidiary of General Motors, showed that they need to have a precise computation graph, which is something that Zenoh-Flow already offers. Then we need also to schedule this computation deterministically. And if you recall the presentation from Christopher, this is something that we're aiming with Zenoh-Flow. So with this, we're also seeing that AutoSAR Classic and Adaptive are a bit heavy. Again, I relate to Christopher's presentation that the developer experience is quite poor, offers little flexibility, and to recall, again, my point on Rust is only in C, C++. So with all of that, we're thinking of future perspectives for Zenoh-Flow. The first is the ongoing work that we're doing with TTTech, which is the custom scheduling. What you can see on the screen is the Rust real-time auto-aware reference system. So what we did is that we enhance our descriptor, so the way we're describing our data flow, in order to provide users the capability to schedule, to say which nodes should execute next. So this is something that we are going to provide in the beginning of 2024, is the ability for users to specify how they want to schedule their computation based on the graph. We're having some preliminary results. So what we did is that we emulated workload on each node. So what you can see in the small rectangles are the computation time we associated to each node. And we ran that on a Raspberry Pi 4. And so what we can see is that we have, on a single core, a theoretical lowest execution time of 12 milliseconds. You can recompute if you don't trust my numbers, but after running this simulation using Zenoh-Flow and our guided execution, we see that our execution time on average on a single core is 14 milliseconds, which is quite close to what we can achieve in theory, meaning that the overhead of Zenoh-Flow is minimal. I have some numbers in my mind, so I would put a grain of salt on them, but I think running the same experiment that TT Tech did using ROS and also using their optimized scheduling algorithm, they reached 60 milliseconds. So we can already see that we're having quite few improvements just by changing the framework. This is great, but we want to go a step further, and we want to provide real-time capabilities. So these real-time capabilities are motivated by the requirements coming from the automotive industry. The first is the ability to park a task. So when we say park is, again, as Christopher explained, if we associate a time budget to a computational node, and then that node overruns that budget, we want to not kill it, but we want to park it on a specific thread that we will run whenever we have free time on the CPU. We also want to assign priorities to tasks. The idea is that depending on your environment, maybe there are some tasks that have a higher priority and you want to execute them first. So Zenoh-Flow will provide a way to do that dynamically. Third point is we want to be able to pin a task to a specific CPU core. Depending on your requirements, depending on where you are, maybe you want to reserve one specific CPU core to one task in order to guarantee safety. Lastly, and because we are called Zenoh-Flow, we also want to integrate with an automotive middleware. Well, this is already done. Zenoh is already in the automotive stack. It integrates very well with Cyclone DDS, so it means we already have a step in there. And with this, I conclude my presentation on Zenoh-Flow. So expect to see this, obviously, beginning of 2024. And Zenoh-Flow, much like Zenoh, is an open source soft initiative. So we're welcoming any contribution.
Okay, thank you very much, Julien. Thank you to all the speakers, and thank you to all of you who resisted to this online Zenoh marathon, because it was an epic marathon. We'll still, hang around here to enjoy some refreshments and keep answering questions asynchronously online. So thank you again for the team. Thank you again for the attendees here. Thank you for the attendees online. And, see you online. Bye, everyone.